I moved to Australia a year ago, and so I'd like to thank the organizers for the special mercy of being able to speak on the second day rather than the first one. When you move down under, you find out what jet lag really is. I've learned one of the ways of dealing with jet lag is to, let's say, gently adjust your expectations for reality. And that's going to be my segue to the talk. All right, so ranks of elliptic curves are a really old question in number theory, and it can be approached from a variety of perspectives. But trying to keep in the theme and the vibes of this meeting, I'd like to try to approach it from a computational or experimental point of view. So we want to use things like big computations, statistics, heuristics to try to understand this topic. And I mean, in the end, what I would like are theorems. But as Birch once quipped, it's often helpful to know what's true before you go to prove a theorem. Hopefully, by the end, we'll come to grips with reality, and soon I'll be on a plane home, adjusting to jet lag again. OK, now, what's an elliptic curve? Well, an elliptic curve is a smooth projective curve of genus 1. It's given by an equation, y squared equals f of x cubed plus ax plus b, where a and b are rational numbers. And the condition of smoothness corresponds to the discriminant, this expression being non-zero, or equivalently the cubic polynomial f of x having distinct roots. Now, the main reason why elliptic curves are so interesting is that there's something called the chord tangent law on an elliptic curve. Primarily, we're going to be interested in this, the set of rational solutions or rational points on our elliptic curve. So the set of rational numbers x and y that when I substitute into the equation, I get 0, together with the points at infinity. And that set by this chord tangent law has the structure of an abelian group. And you can see here, I felt really bad that I couldn't give a board talk, so this is the closest that I got. I wrote on the board and took a picture of it for you, some of the most beautiful equations in all of mathematics. OK, I hope I can say something like that, that describe what this group operation is. And so I'd like to show you a video of what this chord tangent law does. So this is something I collaborated with for Quanta Magazine and by David Song. And here you can see the chord tangent law in action. So you take 2 points, and you draw the line through those 2 points. It intersects the curve in a third point, and you declare the sum of those equal to 0. Equivalently, you can solve for the third point of intersection by reflecting around the x-axis to obtain effectively the group law. And here you see, just starting with those 4 points, or 2 and their symmetric points, their negatives, we're able to generate lots and lots of rational solutions to this equation. After all, if I have 2 points on the curve that I have with rational coefficients, and I draw the line through those 2 points, it will have rational slope. That rational slope will also intersect the curve in a third point. Generically, that third point of intersection, we wouldn't know where it lies, but because 2 of the roots live in the rational numbers, the third does as well. So this allows us to study the set of solutions by generating them from a set of starting solutions. Now, why do number theorists study elliptic curves? It might diverge on a bit of an obsession. I would like to think it's a healthy obsession. Elliptic curves are the simplest equations that we'd like to understand the set of solutions to that are not well understood. So quadratic equations or conics we understand. More variables get more complicated, and these are really the first and simplest ones. They're the simplest non-trivial algebraic groups. So this group law described by polynomial equations are really the simplest ones. I mean, I guess the universe is not an elliptic curve. But maybe some of the dimensions are Calabi-Yaos, and elliptic curves are one-dimensional Calabi-Yaos. So it's also useful in cryptography. Elliptic curves are used in that way, even supersingular or post-quantum cryptography. So somehow, no matter what approach you take to number theory, you find yourself thinking about elliptic curves. And that's really going to be we really would like to understand this set of solutions. That's the main topic of today.
In fact, if I may say, elliptic Calabi-Yaos are the most interesting for phenomenology. So elliptic is important.
Perfect. Okay, now what can we say about the set of solutions? There's a theorem of Mordell that was generalized by Weil, so we often refer to it as the Mordell-Weil theorem. This abelian group is finitely generated. So concretely, what does that mean? Well, there's some finite subgroup called the torsion subgroup. These are points that when you add them to themselves, so p, 2 times p, 3 times p, you get back to the identity element in the group, which is the point at infinity. And then there's a complement to that, a free abelian group of a particular rank called R, the rank of E of Q. And then the group of rational points by this law is isomorphic to the torsion subgroup together with Z to the R, as I've learned to say. Now, torsion subgroups are really cool, but they are well understood. There's only 15 possibilities by a famous theorem of Mazur, and I have a bit of torsion fatigue, so I will not spend more time on that. Today, what we like to understand is the rank. Now, if you're still with me, the rank, in your head, you should keep it in mind. It's the minimal number of points required to generate all rational solutions to that elliptic curve together with this torsion subgroup, which 100% of the time is trivial anyways. And our question is, so what are the possible ranks of elliptic curves? Now, this is the elliptic curve from the video. Here's a picture of the set of points that you can begin to generate. And just to connect all the dots, the torsion of this elliptic curve is trivial, just the point of the identity of the group. The rank is 2, and those are the 2 points that we started with. And I guess I want to show you that there's so much to say about elliptic curves that we have a database of them. So the database is called the L functions and modular forms database. This is your one-stop shop on the internet for all things related to the Langlands program, in case that ever happens. So elliptic curves belong to that program, and here is the elliptic curve x cubed, defined by x cubed minus 4x plus 1 equals y squared. Here you see the Mordell-Weil group, a description of the points, integral points, the same picture that we saw here, and then this is the promise that there's a lot to say about elliptic curves. In case you want to see more, check out the LMFDB. All right. So our question is, what are the possible ranks of elliptic curves? Maybe the first thing we might want to know is it unbounded? And this question goes back at least to Poincaré. Here he is. He also coined the term rank. You can see that in italics, or it is in italics, and then it's, OK, you know what I mean, Romanized. And this is a bit remarkable because Mordell proved his theorem after Poincaré was already asking the question about ranks. It's in a slightly different language about divisors on cubic curves, but it really is equivalent. So this question is about 125 years old. And starting in the 1950s, mathematicians, I put a list here of many people who have contributed to it. Perhaps the one that's hardest to track down is folklore. Not sure exactly where their ideas come from, but still, we're arguing both sides of the question. Are they unbounded? So a lot of times in number theory mathematics, we know the answer. We've done all kinds of evidence to prove that it's true. We know it in special cases, and then it's just like the hard work is getting to a proof. This is a different type of question. We really don't know the answer. Probably if you ask some of the other number theorists in this room, they would have there would be an interesting discussion that would transpire. Okay? So what do you do in a situation like that, where you genuinely don't know the answer? Well, the first thing you should do is to compute as much as you possibly can, or at least that's my instinct. And here is a picture of world records for ranks of elliptic curves. So the most recent one is due to Noam Elkies and Zev Klagsburn, just 2024, last year. And they found a curve with rank at least 29. So that corresponds to the dot all the way on the upper right corner. This isn't really science. I mean, I drew a graph just to make it look like something serious, but it's really not, OK? I guess you could say, what is going to happen to this curve as you go to infinity? But OK, all right. Noam is getting older. OK, anyway. So, but you can see that it starts out low, and I don't know, does this look like a log curve to you? There was a lot of activity in the middle, and it seems to be flattening out. Okay, I don't think that really settled the question, but it sure was entertaining. Yes? It is known, it is very hard to know the rank exactly, but it is very easy to show that it is rank at least 29, and I'll show you that actually in a minute. So maybe we could probably prove that the rank is equal to 29 under an additional hypothesis, which I'll also mention. Thank you for that question. Okay, yeah, maybe that's a good moment to switch to, so I just gave you an equation. Those are enormous. And by the way, if you change one of the digits and shift it by 1, this is not a smooth, continuous thing, right? In number theory, you change one digit, everything completely transforms. To the point where, and I don't really, do you guys notice anything in the pattern of the digits of A and B? I mean, so much so that if, like, as you see, I had to squeeze it on the slide. If I didn't do so well and I lopped off some of the digits, you wouldn't really know. Okay. So we really have to, all right, we're going to have to rely on computers in order to be sure that we don't make mistakes here. So how do you compute ranks? So I'll begin to address some of those questions. We can obtain upper and lower bounds on the rank using Magma. And the algorithms are highly non-trivial to compute the rank. So Jeff Bailey implemented the first version of this maybe 20 plus years ago, and then people have been working on it ever since. So it is not a fast, or there's no new, short, simple algorithm. It is a whole suite of techniques that use a variety of approaches. And maybe I should take this as a moment to mention what is Magma after all, since I was introduced as leader of the Magma group. So Magma is a computer algebra system. It's designed for researchers in maths. Boy, I really have moved to Australia, haven't I? Okay. But the maths there is intentional. It's really plural. It started out as Cayley, which does group theory, but there's representation theory, number theory, combinatorics, arithmetic, algebraic geometry, commutative algebra. There's even non-commutative Grosvenor bases, which you can use to simplify in an exact manner partial differential equations. So it really is trying to hit that spot where it's not meant necessarily for calculus. You know, it's really meant for you sit down, you have a hard question as a researcher, and you would like to explore it using techniques that are appropriate for computer algebra. And about our team, we're about a dozen people. We're based primarily at the University of Sydney, funded by the Simons Foundation. We also have a second location at MIT. So very happy to have to be living that. As was mentioned last night, the internationalization of mathematics is a really important aspect to it. The time zone kind of sucks, but we make it work. Okay, now computing ranks in Magma. So what do? At least we can compute upper and lower bounds on ranks. I mentioned that many techniques are employed, but to give you a sense of what is involved, the technique is called descent. All right, so there's an exact sequence. So you choose an integer m, at least 1. The thing that we're interested in is the thing on the left-hand side. Well, it's a quotient of it by multiplication by m. There's a group in the middle. So it injects into that group, so it's larger than the one. And then there's a quotient. So what are all of these groups? Well, it's easy to show that if m is coprime to the size of the torsion, then we could measure the rank by understanding the size of the abelian group. That's the thing that we're interested in on the left-hand side. The thing in the middle is called the M-Selmer group. This group is a computable finite abelian group. Wouldn't that be great if those two groups were just equal? Well, there's not. They're not always. There's the error term, so to speak, in this exact sequence is called the Tate-Schaffer-Ravitch group. The Tate-Schaffer-Ravitch group is, well, it's the M torsion, I guess, as mentioned in the exact sequence. This Tate-Schaffer-Ravitch group is conjectured to be finite. So if it was finite, you could choose M coprime to the size of Shaw, and then these two groups would be equal. Okay, unfortunately, we do not know the finiteness of Shaw. So the bad news is there's no provable algorithm that takes as input the elliptic curve given by its coefficients a and b, and like a Turing machine produces after some finite amount of time the rank or description of the set of rational points. And that is a real bummer, but there is, if you assume the widely believed conjecture that this Tate-Schaffer-Ravitch group is finite. So in practice, what happens is you compute and you get upper and lower bounds. So the upper bound is the size of the Selmer group. The lower bound is whatever you can find by searching for rational points in the first place. And then when they meet, you're done. And when they don't, I guess you have some more work to do. Now, no, it does not. I think that I think that is conjectured to be arbitrarily large. And in fact, that is such a good question. Eventually, you want something that would allow us to understand or predict quite generally all the terms in this exact sequence, what we should be expecting from it. And that will be topic number 3 towards the end. Okay, yeah, so that's great. That's really the right mentality to have. What should we be expecting from the terms in this sequence? Okay. Now, right, what I was saying, these algorithms are sped up by assuming something called the generalized Riemann hypothesis. I'll say a little bit about what this later is. I promise you this is not the, this is the least objectionable thing that I might ask you to assume over the course of the hour. All right, so try it out. I don't know, I'm going to try a live demo. You never know how that's going to go, but. So this is Magma. I'm running on a server at MIT just because although it was, I was willing to get on a plane to come all the way here, the bits coming all the way from Australia would be too slow. So here's how you might define an elliptic curve in Magma. You see the one that we were computing with earlier. And the command is called rank bounds. And in this particular case, in 0.1 seconds, you can find that the lower bound for the rank is 2, the upper bound for the rank is 2, so the rank is equal to 2. Now, that's a pretty small elliptic curve. The coefficients are called 4 and -1. Are we almost to the Elkies-Clausenburg curve? OK, how much harder is it going to be to understand that particular elliptic curve? Well, here's one which, can you guys see that? Is the font size big enough? OK, is that better? OK, so here I took the elliptic curve with a coefficient of 1,000 and another coefficient of size with 5 decimal digits. And here it is at work. So it's, first of all, it checks the torsion subgroup is trivial. And then it says the 2 Selmer group has rank 2. And that means that the rank is between 0 and 2. And here it is, this SHA, which is Z mod 2 squared. Or at least it's a subgroup of. It's not sure whether that additional contribution in the Selmer group comes from rank or from SHA. So it goes a little bit farther, and it says, well, perhaps we should look at 4 descent. So this is changing the M to try to dig a little bit deeper and understand that, try to decide about SHA. Fortunately, it was not able to resolve the issue there either. You see Z mod 4 squared. It searched as much as it could to find rational points. It couldn't conclude. And so after 14 seconds of effort, it tells you the rank is between 0 and 2. Now, I don't know how you guys feel about the sizes of these coefficients. They look pretty innocent to me. And we went from 0.1 seconds to 15 seconds. Okay, so it is not realistic. If we ran this on a much larger, it's effectively going to run forever. Now, the question of showing that the rank is at least 29 is just the lower bound. So here it is. This is the world record example of Noam and Zev. So there's the coefficients. OK, I put plus xy. That's a slight change of variable to complete the square. But here are the x coordinates of the points. I asked for the corresponding y coordinates. And then I asked, is linearly independent? OK, and the answer is there are 29 such points, and they are linearly independent. And that's enough almost instantaneously to know the rank is at least 29. And it's sort of hard to believe that it isn't 29. It would. I mean, if we're just trying to understand what to expect from this, it's like, oh, maybe it'll be 60 because additional solutions will magically transpire. No, generally Diophantine equations, the vibe is they don't have solutions unless they have to, unless they're forced to for some reason. And here, well, I hope that addressed your question about, it would be a lot more effort, but it's a lot easier to do this. All right, so that's Magma in action. I hope I've convinced you or helped you to understand what the complexity of the topic is. We are interested in ranks. We have a proxy for them in the Selmer group. We believe that the error term, the Tate-Shafarevich group, is finite, but we're not able to resolve that in theory or in practice for large enough examples. OK, so maybe it's time to shift our perspective. adjust our expectations for reality. Now, we just spent some time looking for the brightest stars in the heavens. And that's an important task to do when you look up in the sky. I guess I would like to say, well, let's understand the heavens itself. So really, not just what the largest possible ranks are, but really what the distributions of ranks of elliptic curves are. So that is not going to directly answer the question, are the ranks unbounded, but it will try to address broader questions about the arithmetic of elliptic curves, and then hopefully bear on the question of ranks. So what does it mean to talk about the distribution of ranks of elliptic curves? There's infinitely many of them, so we're going to order them by size, cut off the size, try to decide a property of them, and let that size go to infinity. Okay, so here's my elliptic curve. I'm going to try to write down a unique representative up to isomorphism that allows me to measure the size. So I do that by first shifting my coefficient. I change variables, rescale x and y in a minimal way. So what does that mean? Well, I can clear denominators so that the rational numbers a and b are in fact integers. But I do so in a minimal way. So if I happen to rescale x and y by both by a p cubed and a p squared in order to get the p to the fourth, then I could divide out again. So what that boils down to under this weighted homogeneous action of the primes is that you ask that a and b be integers, but there's no prime p such that p to the fourth divides a and p to the sixth divides b. And once you do that, then these integers a and b uniquely determine the isomorphism class, and every elliptic curve appears in this form. So if you want to think about, you can almost forget about the elliptic curves from this point of view, and just think about pairs of integers a and b with this slightly more interesting GCD condition. Okay? With those, it's reasonable then to decide that the height of the elliptic curve or its size is basically the size of a and b. However, we saw that there's a kind of weighted action. In order to get the leading coefficient to remain to be 1, you have to shift the x by a cube and the y by a cube and x by a square, and then divide out by a sixth power. So when you do that, you want to remember the weighting on the variables. And so we define the height of E naturally, I think, just to be the largest of the two coefficients that appear in the discriminant of the elliptic curve. You guys remember the 4a cubed 27b squared? And that is, of course, the discriminant itself might be smaller because if you have two integers of a given size, they might cancel. And so the discriminant might be smaller than the height. But usually that doesn't happen. The height is well approximated by the discriminant. Now, the height really isn't our favorite measure of size. Really, the right measure of size is what's called the conductor. It's the right measure of arithmetic complexity. I'll show you later why. But honestly, it's just a lot harder to work with. As far as this experimentalist mindset that we have, the conductor is pretty close to the discriminant most of the time, and the discriminant is pretty close to the height. And we would like to believe that that isn't the most important thing when we're trying to understand ranks and their distribution. Right? So although I would like to have theorems or do experiments with conductors, I hope it's OK, this more naive notion of size, at least for us to get our bearings. That's the approach. All right? And so here's a random-looking elliptic curve. Even those coefficients don't really look that big. But the height there is 2 times 10 to the 19th, and the discriminant is about 3 times 10 to the 20th. So those are about the sizes that you should have in mind for when we talk about heights. OK, so here's what was on the previous slide. Here's how we're going to understand distributions. We're going to take the set script DE to be those pairs A and B with a given condition, and then we're going to take less than or equal to h, say that that height is at most h. So that's now a finite set. How big is it? Well, if I want a cubed to be at most h, then a needs to be about cube root of h. Similarly, with the b, it should be at most about square root of h. So that means I have about h to the 1/2 plus 1/3 is h to the 5/6 possibilities. So that's the very easy, fast thing I can say about elliptic curves by height, whereas computing them by conductor, I would have a very long conversation to have with you about how many there are and what our predictions are. Okay? Now, the 2 to the 4/3 and 3 to the 3/2 is because I have coefficients 4 and 27. That's not really essential here, but it is the choice that we make for our heights. And the zeta of 10 is because of this condition that I asked that p to the 4th doesn't divide. There's no p such that p to the 4th divides a and p to the 6th divides b. So it's like a sieving factor that comes out. So more or less, it's about half times h5 to the 6th number of elliptic curves up to isomorphism in our up to height h. And now we have a precise question. What is the distribution of ranks of elliptic curves E in this set as h goes to infinity? Does that limiting distribution exist? What does it look like? What can you expect from it? That's the more precise version of our question. Now, there's a minimalist conjecture. To set it up, I have to introduce one new piece of information about an elliptic curve, and it's called its sign. I'll give you a little bit of a sense of where this sign comes from, but in order to set up the conjectures and the expectations, that's not essential to know. Every elliptic curve has a sign, plus or minus 1. It's much easier to compute than everything else, certainly way easier to compute than the rank. And there's a conjecture that the sign is related to the parity of the rank in the following way. Minus 1 to the rank is equal to the sign. I'd elaborate more on where this comes from, but it just says if the sign is plus 1, we expect the rank to be even. If the sign is minus 1, the rank is supposed to be odd. So in the example that we just looked at where the rank bounds were 0 and 2, the sign of that happens to be plus 1. So it's still 0 or 2. If the rank happened to be minus 1, then and you believe this parity conjecture, then you know the rank had to be odd. And so actually from that data, we would be able to conclude that the rank was 1. So that's where this conjecture really makes a difference. And here is the conjecture. It's called the minimalist conjecture, and Goldfeld, who's here, was looking at quadratic twist family, so I attached his name to it. So as h goes to infinity, the minimalist conjecture says we shouldn't expect more than what the sign requires there to be. If the rank is even, then it should be 0. If the rank is odd, it should be 1, and all the rest of the time, that's negligible. Okay, so half and half, rank 0 and rank 1. And if you want, here's the absolutely precise way of saying that limit. So the limit exists, and it's a half 0 elsewhere. So are you guys glass half empty, glass half full kind of people? This is your, it shouldn't, that's what I'm saying about like Diophantine equations shouldn't have solutions unless they have to have them. Okay, this is kind of a way of quantifying that. One interesting consequence of this is that the average rank of elliptic curve, so you just, as a particular statistic that you might take from the distribution, the average rank is a half. All right, now let's test that minimalist conjecture with some computation. So that's what I was trying to set up to finally get us to here. So in 2007, Bauer Bechterhoff, Barry Mazur, William Stein, and Mark Watkins reviewed, they had a data set. This data set was ordered by conductor. And as you see, the data goes out to e to the 19th. Okay, so that isn't quite 10 to the 19th. So that's smaller than the curves that we looked at, the example curve. So the coefficients are not enormous. And, well, do you guys see support for the minimalist conjecture? It doesn't look good from this data. It's supposed to be tending to 50-50 with the top two. And yo, it's not. It looks like rank 2 is going up.
So for these elliptic curves, do they know all the ranks of all the elliptic curves?
That's right. We did a complete database. I'm not sure if in the Stein-Watkins curves, yes, they computed all of the ranks for all the curves in that data set. And OK, well, that should cause you some worry. About 10 years later, we shifted our approach. Instead of doing all elliptic curves, we sampled, which I think is a better thing to do statistically. So they started out by computing all of the curves. We also shifted to doing height instead of conductor. Okay, so what do you order them by height? Notice the height goes out to 10 to the 10th. So in terms of sizes of things, that's like 10 orders of magnitude smaller than the one that I showed you, which looked pretty small. Okay, but at least if you finally go to 10 to the 10th, then you see the numbers start going down again. Notice, though, the scale here. So it was like creeping up to about 17% of curves, and you go farther out, and it looks like it's now down to 13.5%. Okay, at least we saw it going back down again. We looked at this. I guess you should do this experiment every 10 years. Okay, so this was 2016 in an ANTS paper, so time to do it again. But we got to go big. Okay, so let's. We decided to do some computations on much larger scales. Okay, some new data. So this is with my PhD student, Blair Butler. Here he is. And we took 10,000 random elliptic curves. It's not hard to get a random elliptic curve at a given height, just to generate the A and the B in that size from my set E less than or equal to H. And we did it for 10 to the n with n from 10, which is more or less the left-hand side, all the way up to 10 to the 45th. And, well, I told you we have to assume some things. So the parity conjecture and GRH are two of the things that I will assume when we do these calculations. So it's really helpful it speeds up the algorithms. All right, bye, Blair. We're going to show your data. So here's the debut of the data. Now, I remind you that sometimes we can't compute the rank. We only have bounds. So what you see on the left-hand side is the lower bound. So for example, the main issue between the left-hand side and the right-hand side is the blue curve, the rank 0 curves. On the left-hand side, they are tending up to a half. On the right-hand side, they're kind of staying flat. That's the high estimate. And similarly, the rank 2 curves here, they're tending nicely to 0, and on the right-hand side, they're staying constant. Okay, so this is more or less like about 10% of the curves either have rank 0 or 2 and sign +1. And that quantifies maybe the difficulty of the problem that we're facing. So the minimalist would say that all of those curves have rank 0, and if so, then we have a pretty nice distribution of things. We can't simply run Magma longer on these curves. So I remind you that this is a 10 to the x scale. So the data that we looked at from 10 years ago is just like the 10 to the 15th, 16. That's all we were looking at. So we went 30 orders of magnitude higher. So effectively, the curves of height 10 to the 45th that we are looking at, we have to peer out far enough into the universe to really begin to see the background radiation, gravitational waves, however you want to think about that, okay? But our instruments are not going to give us the exact answer for those curves, all right? So we expect that the low estimate is correct. And I want to tell you some reasons why. So there's an analytic approach to ranks. So I'm sorry, there's going to be like maybe 2 slides with technical formulas, but is sort of to try to convince you that after we see this data, that we know what the next step is, and it really should lead us to believe the low estimate. Okay, so if E has large rank, then the number of points should be larger than usual. Lots of points can be generated. And so we consider the rate of, Birch and Swinnerton Dyer in the 60s considered the rate of growth of the function where you count the number of points mod p, with a congruence mod p. You take the product of those divided by p, which is the expected number, and look at the rate of growth of that function. Okay, that led to their conjecture, which I'll state in a second. Instead, these days, we define what's called the L series of the elliptic curve. The coefficients are defined by the number of points, shifted in this way, minus the expectation. And the product that you're looking at is 1 over the specialization at 1. This, if you haven't seen L series of elliptic curves before, is analogous to the Riemann zeta function. The Riemann zeta function has lots of good properties. In this case, because elliptic curves over Q are modular, we know that if you extend the L series in this particular way with a complex gamma function and a power of the conductor, that it satisfies, that it's an entire function, extends to the entire complex plane, and satisfies a functional equation. You see that it appears the root number that showed up in the parity conjecture. And the GRH here is like the Riemann hypothesis. The non-trivial zeros appear on the critical line. That is the line where s is equal to 2 minus s, the real part. So that's real part s equals 1. And the Birch and Swinnerton Dyer conjecture is that the rank is equal to the order of vanishing of this complex analytic function. And in particular, the function is either even or odd, depending on the rank, at s equals 1 when you write it as Taylor series. And that is the reason why we expect the parity conjecture, something even. Okay, so that's the analytic approach. And now there's something called the explicit formula that comes out of understanding of L functions. I'm going to apply it with a Gaussian because those showed up a couple of times over the course of the last 2 days. And it goes like this. So the rank is going to be bounded by the following thing. I have to assume the GRH, but then I'm going to sum over all of the non-trivial zeros with multiplicity of the L function. So if you believe the Birch and Swinnerton Dyer conjecture, that includes the order of vanishing at s is equal to 1, which will be the rank. And then there may be some other contributions to this, but the exponential function is non-negative, so that I get a less than or equal to. The functional equation, expresses this as explicitly as a sum of an expression involving the log of the square root of the conductor, some explicit integral, and then a sum. This sum is given by the coefficients of the L series, just the prime powers, weighted in this particular way by a Gaussian function. As a goes to infinity, we get a better and better approximation. The Gaussian sloops just to be supported at s equal 1. So if we took a to infinity, we really should be able to compute the rank this way if you assume, the well-known properties of L functions. But there's no way we will be able to evaluate SA. We need way too many coefficients to get the right. So I compute this on the right-hand side exactly, or with a different test function with compact support, then it's too hard, too computationally hard. We're still stuck if we want to know the actual answer. But the thing that we did, which I'm really excited about, is to estimate SA. So what do you need to know? Well, you need to know the variance of this sum. That variance can be computed using what's called the Sato-Tate distribution. So if I told you what the variance was, then I can divide up the interval into fixed amount of variance, sample within those intervals, and with some reasonable confidence, 95% probability, tell me how many samples to take, I can estimate the right-hand side, which gives me an estimate for the rank. And this is still work in progress, but it really does seem to confirm the low estimate, and it really gives us a new approach to thinking about what the rank is. It'll never tell us rigorously what the rank is, but it looks like it's telling us the right answer.
You still have to assume very certain.
Yeah, we have to assume everything. Yeah, BSD in particular, and GRH for the L function. That's right. But wouldn't it be nice if I could tell you what the rank of one of these larger elliptic curves is, even though it's not a theorem? I mean, I would still like to know the answer. Okay, great. I'm about to shift up the vibe, so I would love if there are any other questions. Yes? Yes? This one here. So it's all of them up to a given height on the blue curve, and then they sampled the dots, a certain number of curves. Correct. They might have assumed GRH because they used an analytic approach sometimes. No, I don't think they needed the parity conjecture. They assumed GRH and BSD, which in particular would imply the parity conjecture. Another question. Yes?
I just want to remark that the first person to compute the rank 2 curves was Zagier. He did it up to like 2000, conductor 2000, and like 40% of them had rank 2. And there was a period when nobody believed the minimalist conjecture.
Yeah. I mean, I really do feel like we took a microscope and now we're looking at a telescope with elliptic curves. So what we need to do is to fix up our telescope to kind of take the information that we can compute from it and really convince ourselves that this is true by not looking at such a small data set. That's the... You guys have funding for that level of infrastructure development? You heard it. You heard it. Okay, great. Now, having done some computation and some statistics, I'd like to now think in terms of heuristics. I promise you I'm a pure mathematician, even though it doesn't sound like I am, okay? So what is a heuristic in number theory? So what we'd like to do is to have reasons to believe, like what should we be expecting from that distribution? How do the pieces of that exact sequence go together? We want like some mental model or a computational model that allows us to understand this really hard, arithmetically sensitive kind of quantity. Okay, so we're going to build a math model. That's what we do, right? It just happens that they're elliptic curves. Like any good model, it should be as simple as possible, but no simpler. Okay, so this is joint work with Jennifer Park, Bjorn Poonen, and Melanie Wood. And the model is a linear algebra-based model, and it predicts that ranks are bounded. Okay. Now, I don't know whether ranks are bounded, but I can tell you by theorems that I have a model that predicts what we know about the arithmetic of elliptic curves. Like it recovers things that we know are theorems or see as computations. And that model predicts that ranks are bounded. So I feel like we should do more of this in trying to understand. Refine the model, test, it really, okay, that's the scientific mentality. Okay, now what does it look like to build a model in number theory? So for example, is this integer prime? Sort of an analog for a question. What's the rank of this elliptic curve? The answer is, oh, well, I don't know. Yes or no is the answer, and you have to compute. But really when you're asking a question like that is, what's the probability that a number of that size is prime? Okay, well, the prime number theorem says if you count up to x, the probability that a number of that size is prime is 1 over log x. So if you want to model the set of prime numbers, now that's a deterministic thing. A given integer is either prime or it's not. But if you don't want to think about individual integers and you want to try to make predictions relevant without actually checking those, then the CAREER model says choose a random set of integers and each one is prime with probability 1 over log x. Okay, now that's a terrible model because any two consecutive integers, at most one of them is prime. Because at most one of them is even, all right? So you have to be careful about what types of questions that you ask about models like the CAREER model. They don't give you an answer to everything, but they do great with things like twin prime conjectures, and if you wanted to just like, well, it gives you a way to make predictions. Are there infinitely many, for example? That's what this type of thing should be good for, and we're gonna apply the same methodology for elliptic curves. Now, you guys remember the exact sequence. There are theorems and widely believed conjectures on the expected behavior of the M-Selmer group and the M-torsion in the Tate-Schaffer-Ravitch group. And here I've summarized it to you as well as I can in one slide. As M goes to infinity, what you do is you take a random alternating matrix, so the transpose is the negative. You take entries in Z mod MZ. The size of the matrix N goes to infinity as well. So you have to be a little careful about what's going to what with some order, but I'm just giving you the idea. And the answer is the Tate-Schaffer-Ravitch group is modeled by the co-kernel of this random matrix with integers in Z mod M, but with growing. So, and E mod M, which is the proxy of the rank, is modeled by the kernel of this matrix. Okay, so I'm just going to put what I just put. So this is the beginning of trying to understand what arithmetic is. So again, theorems and widely believed conjectures tell us that this is a reasonable place to start. So if we want to understand E of Q mod M E of Q, so what you have to do is like is modeled in this particular way by kernel and co-kernel of a random alternating matrix with entries in Z mod M, M and N going to infinity. All right, now our idea, the key idea, of which all this is, well, okay, M is going to infinity. That's telling you about M primary parts. Let's model it by an integer matrix instead of Z mod M's coefficients. And we're going to tune that matrix so its size and the coefficients that you take in that matrix are related to the height of the elliptic curve. So it's like lifting from information that's about M as M goes to infinity and trying to globally understand it through an integer matrix. Okay? Yeah?
What do you mean by taking a limit as M goes to infinity? Because
yes.
if there was a limit, I could take the limit through prime, and then something weird happens. The kernel and the
let's see, what can I say? Most of the time, because of the Sun-Si Chinese remainder theorem, or CLO subgroups, we're only really interested in prime powers.
Okay.
So not always, but you have to be careful how you take your M's, and in all the statements that I just took, M is usually a prime power, and that power goes to infinity. Is that enough for you to be happy? Okay, great. That's a consequence of me trying to simplify, but I made it too simple. Okay. Now, what about the size of the matrix? As you guys know, alternating matrices, it's really important to know if the size of that matrix is even or odd. odd alternating matrices automatically have something in the kernel because the determinant is, okay. So the way to deal with it, the way that I like to explain, is that the size of the matrix is modeled by some function going to infinity. So here I put log h, but for all intents and purposes, it could be any function slowly growing. And then the size of the matrix has to be an integer, and it doesn't know whether it's supposed to round down or round up. And that explains why there's a sign. Okay? So it makes a choice there whether it takes the lower upper bound. Okay, yeah, that's the floor and the ceiling. The sizes of the entries are uniformly random in integer entries in some function x of h. And the way that we tune the model or normalize the x's and the n's for a given height uses rank 0 BSD. So again, things that we know, or if you want to think about experimental observations that we have made that the model has to represent reality, and it tells us this is the scale that we should be using. It's x to the n combined rather than them separately, but I just wanted to make it concrete to see what it looks like, and it's about h to the 1 over 12. So if we're going to be compatible with what we know about distributions of Shaw's and why they predict it, then this is the scale to take. And then here's what the model states. Just like mod m, the rank of the elliptic curve should be modeled by the rank of the kernel of this random matrix. So here's how this would look in our running example. So here's an elliptic curve with some coefficient size a and b. You compute this n, and it's between 3 and 4. It flips a coin. It says, OK, I'm going to round up this time, so I have to make a 4 by 4 matrix. The sizes of the entries are about 2.5. And so then I have an alternating matrix, and I say, what should I expect, just like whether this integer is prime or not, what should I expect for the rank of this elliptic curve? Well, it's probably like the rank of this matrix. It's a linear algebra model. Does that make sense? OK, now the good thing about this model is that it predicts the minimalist conjecture. So most of the time, matrices, an alternating matrix, as the size goes to infinity, entries go to infinity, the determinant is 0 100% of it, non-zero 100% of the time. And so that's why the only time you get rank 0 or 1 depends on the size of the matrix. We also, for r is equal to 0 and 1, recover predictions for the size of the Shaw as co-kernel. And because we talked about reducing mod m, because I'm taking my integers uniformly random in some range, as m goes to infinity, I'm recovering all of the theorems and conjectures that I said framed our model. Because if I look at their images mod m, just reduce my integer matrix mod m, then I eventually, with the size of the matrix and the fixed m, recover the original prediction. So it really is trying to globalize it with integer entries. OK, and then there's a theorem. So the theorem says, what does this model predict about ranks? So now you need to count the number of alternating matrices with integer entries in a particular size, and what is the probability that their ranks are a given number r. Okay, but that's a thing that you can really do. We generalize the theorem of Katz-Nelson. And it says, so if you put these together, the probability that the rank is at least r, we believe is related to the probability that this random matrix has rank at least r. This is how many you get. So the number on top is the number of such integer matrices with kernel of rank at least r over the total number of such skew-symmetric alternating matrices. And OK, you simplify, and then you plug in our normalization. The x to the n is h to the minus 1 over 24, 1 over 12. You remember that the number of elliptic curves, so this is really an effect. It's like, what's the probability that an integer is prime? It's 1 over log x, an integer of size x. What's the probability that an elliptic curve has rank at least r? Well, it depends on the size of the elliptic curve, and if the size is about h, then that's the probability. Okay, so now you want to know, are ranks bounded or not? We have to count how many elliptic curves are there. So there's about h to the 5/6, like we talked about before. And then you apply the Borel-Cantelli lemma that says when you take the sum of all the probabilities, if it converges, then it happens finitely many. If it doesn't converge, then you expect it happens infinitely many times. And when you do that calculation, it says all but finitely many satisfy rank less than or equal to 21. Now, 21 has to do with the 20 over 24 in a straightforward numerical way. And as it turns out, this is also the prediction of Andrew Granville and Mark Watkins, who did something completely different about ranks. looking at the shape of the Mordell-Weil lattice and some other estimates on integer equations. And you know what they got? They also predict bounded, and their bound is 21. Does that make you believe it now?
This is a proof or is it?
No, all heuristic conjecture. We're just trying to decide what's true.
So some of the examples we heard earlier, like greater than 29, or those are really exceptional.
Yes, that's what this model predicts. There will only ever be finitely many of those. And therefore, the rank will have to be bounded. OK, here's another. So now you do other experiments, right? So you say, OK, now you have a model. It's going to make some other predictions. So remember I said never mind about the torsion? Well, if you ask not all elliptic curves, which would be the top one, but you say, let's look at all elliptic curves with a fixed torsion subgroup. Here's the list of 15 of them. You run our model. So what are the approximate sizes when you plug in? And our prediction for the all but finitely many is in the third column. And you compare it to the efforts of lots of people over a long time about whatever they can do to show infinitely many elliptic curves with that torsion subgroup. And so the numbers on the left-hand side are always less than or equal to, the numbers in the fourth column are always less than or equal to the numbers in the third column. And that's some kind of evidence for our conjecture. The stars are because there's quadratic twists, and so sometimes you can make 4, but that's OK. And now, this is, again, not a serious slide, but it's the thing that I would like to be able to do at some point. So you guys remember the low estimate data? That's the solid lines. If you just super naively, you don't try to fit some little o of 1 terms, don't even think about the constants, OK? You end up with the dashed lines from our heuristic. So they're not to be taken seriously. They're taken in a very rough sense. Then, I don't know, looks pretty good, doesn't it? We're not ready yet to try to fit constants or anything like that, as I hope I convinced you. But there's the chance that we're telling a consistent story this way. All right, almost at the end of my talk. Of course, another question that also showed up in a lot of the other talks is, well, what does machine learning or what AI can tell us about ranks?
Can I ask some questions?
Yes, yes.
Does it make sense to also try to look at study correlation of ranks? So these are like distribution of ranks, but you can also consider endpoint function.
I guess our model is saying that those are independent.
So that's a prediction of your model?
Yeah, I guess so.
OK.
I think there is some correlation that shows up in that crazy formula. There was a sum S with the APs, and would like to, if we're going to do some more stats, then we're wondering about some of the correlations of the APs. I think there's lots of good statistical questions asked there. OK, what can AI tell us about ranks? This is one slide as an apology that I'm not able to go into it here, but I'll tell you one thing. So a team of researchers with a paper that was published in 2025 they plugged in all of the elliptic curves from the LMFDB. They took the APs and the ranks, and they said, what can you tell us, machine learning? And they found, almost by mistake a little bit, a subtle rank-dependent regularity in local averages of the APs. They call this murmurations after the behavior of a cloud of birds in the sky. They tend to congregate in certain ways in a cloud-like but regular distributed pattern. And so this is the left-hand side, shows you the averages of AP. The blue, why do we always do blue and red? OK, blue is rank 0, red is rank 1. No political affiliations either with the elliptic curves, I promise. And here on the right-hand side, so do you see how if we corrected for the rank, that it really is kind of even independent of the rank? Here you see on the right-hand side what you get from rank 0 and rank 2. The rank 0 is blue and rank 2 is green. And so there was something that we were missing in the average behavior of APs that was discovered by AI. And these patterns might suggest or guide a statistical approach to ranks. It makes us wonder what other hidden numerical whispers about ranks remain to be uncovered, buried in the L functions. I don't know. This is a very active area of research, very exciting. And I hope that more will emerge from it. And in conclusion, I tried to tell you about ranks of elliptic curves. What's the rank? It's the number of generators required to produce all the rational points. We don't know how large the rank can be. We're haunted by the phenomenon of what looks like rank 2 curves owing to Shaw, but there's some statistical estimates that we have made that really do suggest that the minimalist conjecture is true, and I hope that sometime soon we'll be able to guess ranks rather than always asking what a rigorous algorithm can give. We also proposed a heuristic, which I think of like an Occam's linear algebra razor that tries to understand, broadly speaking, what to expect from the arithmetic of elliptic curve, because they can answer questions like, what do we expect from the size of Shaw? So that would be predicted by the determinant of this random matrix, for example. Curve E's, okay, yeah, that second E is jet lag. And the main point that I want you to take home is that the heuristic predicts, but it's really a theorem that the ranks are bounded by 21. The way that I think about this is like it's like with probability 1, ranks are bounded. In the multiverse, there is a universe, most of the universes out there, ranks are bounded. I still don't know about this universe, okay? But that's the best we can say. And I don't know, it could still be that there are special families that behave differently for different arithmetic reasons, and so the mystery, we remain captivated by that. Thank you so much for your attention.